You are watching GrassRoots Community Television, helping you make television people watch everywhere. Broadcasting on cable channel 82 in Glenwood Springs and Carbondale, and channel 12 in Aspen, Snowmass, Basalt, and Elgibel. Free over-the-air broadcasts throughout the Roaring Fork Valley. All programs can be watched anytime, anywhere at grassrootstv.org.
Well, hello everybody. My name is Nick Sampson. I'm a naturalist here at ACES. So welcome to the 8th Naturalist Night of this winter season. First off, I'd like to thank Wilderness Workshop as well as Roaring Fork Audubon for working with ACES to put these great presentations together. I'd also like to thank Two Leaves and a Bud for donating their delicious tea for these wonderful occasions. So tonight we're very lucky to be joined by Jeff Deems. Jeff is a research scientist at the University of Colorado in Boulder. His research focuses on the dynamics of snowpack, snowmelt, and avalanches in mountain environments. And through his work, as well as his lifelong passion for skiing, Jeff spent quite a good bit of time in the backcountry as well as in the field, experiencing these snowpack issues firsthand. So, and Jeff is actually just arriving back to Colorado from Hawaii, and he spent the majority of today, this beautiful snow day, trekking through the majority of the state trying to get to Aspen, so to make it here with us tonight. So please join me in giving him a very warm welcome.
Thanks, Nick, and thanks to all of you for showing up on this, what's proving to be a treacherous driving evening out there. Yeah, somebody had to go to the tropics in order for the snowstorms to start coming in, so you're welcome. I'll be taking a collection later for offsetting my travel costs. Anyways, really a pleasure to be back here at a Naturalist Night. Thanks to Jim and the ACES staff for the invite. Tonight I'm going to talk a little bit about some of the factors that are changing the snow hydrology of the Upper Colorado River Basin. I've given a talk here before specifically about dust on snow, which has been sort of a hot topic in the past few years, or certainly a very visible one. And some recent questions are arising, or more recently some questions involving the Mountain Pine Beetle infestation and the climate change that is ongoing as to how much those factors are affecting the snow accumulation and snow melt in the Colorado River. First, a couple of examples. 2009, in early April, this is an avalanche path down near Silverton that nothing particularly special about it other than that it's easy to photograph from leaning out of your car window. And so you'll see April 5th looks nice, bright white, full coverage. There's several meters of snow on the ground there. 19 days later, and by May 18th, it's all gone. That was reflected in the instrumentation. This is a SNOTEL site in the upper Rio Grande, but right in the middle of the San Juan Mountains. And this shows snow water equivalent. So if you melted the snowpack down, how much water that would be. Over the course of 2009, the red trace is the 2009 year. The black line is the mean over the the full period of record mean for this site, and the gray areas are the range of variability at this site. And you can see that we had near average peak snow water equivalent right around the right time of year. So if you're sitting at this point during the year, it's looking like a pretty average year in pretty much every respect. We had the earliest meltout date on record in 2009 at this site. Many of the other sites statewide had a similar extreme snowmelt season in 2009. This is Lake Mead in 2010. normally when you see the pictures of the full pool, the water's right up at the top of these towers. So pretty low pool elevation. And in fact, it was only 7 feet away from a level 1 shortage declaration, which would have triggered all kinds of legal ramifications basin-wide. We don't want to get there and explore what the legal situation looks like if there's a call on the Colorado River Compact or any of these other important levels. We've since come back up thanks to the fat snowpack of last year. But people were getting pretty worried here. This was the lowest Lake Mead had been since they filled it. So that's pretty telling. Boulder Creek, Front Range, just uphill from my house. Spring of 2010, we had some hot temperatures and a big snowmelt flood came down the canyon and took out the bridge to the Red Lion restaurant. In fact, it's a culvert-style bridge, so it's 2 big tubes with sort of some infill in between it. And before it actually ripped out, the water was ponded up behind it. And so they evacuated the river corridor in town, fearing that there was going to be a catastrophic release and take out people down in Boulder. Here's the peak flow. The averages for that time of year are way down low. So this was a pretty extreme snowmelt. The media was blaming it on the hot temperatures. It was 80, close to 90 degrees in Boulder. So I'll come back to these stories in a little bit, but what we're seeing is some strong perturbations to the snowmelt cycle in the past several years. And it's really grabbed the attention not only of the public through events like this that are very visible, but of water managers throughout the upper Colorado River Basin. One of whom is Denver Water, and they manage Lake Dillon. And in 2011, there was a huge snowpack, and because of 2010, when they had Dillon Reservoir close to full, and then all of a sudden the snowmelt peak came out way higher than forecast. And they had to open the floodgates on Dillon Dam. And it looked just like this. This is from last year because they were draining the reservoir in advance of snowmelt. But they had to, in pretty short order, make some room in the reservoir so that the snowmelt pulse didn't overtop the dam. And so this is just downstream of the outlets, if anybody goes shopping there. So that's a lot of water. There's a lot of houses in the stream corridor down there that were, you know, the discharge that they were hitting there was 1,800 CFS, which is their stated maximum. They don't like to get above that because it does start flooding some infrastructure in some of the shopping areas down there and some of these homes. So Denver Water's had a couple of nervy years with Lake Dillon, and they came to us at the Western Water Assessment and said, what the heck is going on? We've got peak stream flows that are outside the forecast range. We've got dust on the snow. We've got what looks like an anomalously low elevation snowpack in one of these years. We've got bark beetles up in the Snake River. Which of these is it? And going forward, what do we pay attention to? So this was, as a scientist, this was an interesting call because this is direct stakeholder engagement, we like to call it. This is a call for applied science, and I love that because it's not just ivory tower stuff. This is something that we could actually provide an answer to somebody, even a qualitative one that says, yeah, if it's a heavy dust year, look out, or yeah, the more bark beetle infestation you have, look out, or something like that. Even something as vague as that would help water managers. So backing out to look at the full Colorado River, the Colorado River provides water for 30 million people in 7 states and 2 nations. And currently, demand is outpacing supply. This is, sorry, it's a bit of a poor resolution graph. The blue line here is water supply. It's a 10-year running average, so it's a bit smooth, missing some of the year-to-year variability. And then water use is this red line, and you can see where they intersect. Supply equals demand, and now the red line is above the blue line, which is not good. Projections on the right, those are purposefully fuzzy to try to convey some uncertainty there. But nonetheless, the projected demand clearly increases, and projected supply, even if it stays flat, we're in trouble. So The Colorado River is pretty interesting, though. The majority of the flow in the Colorado River comes from snowmelt in the upper basin. So that's us here in Colorado, some Wyoming and Utah terrain, and a little bit out of New Mexico. And then down in the lower reaches where the majority of the big straws are taking water out of the river, there's not a whole lot of inflow. So that's known as an exotic river, something where the water comes from somewhere else. It doesn't come from the area that the river flows through. The lower basin, the California, Nevada, Arizona, has a storage in Lake Powell and Lake Mead and some of the other reservoirs further down, equal to about 4 years of annual flow of the Colorado River. So there's a little bit of buffer there. But an extended drought can really start to work its way into that backstop, if you will, and that's what happened with Lake Mead in 2010 and leading up to that. In the upper basin here, we don't have very much storage, and for water needs here, whether it's transbasin diversions going to Denver, or whether it's western slope agriculture, or municipal use, et cetera, we really rely on the snowpack as a reservoir. We can store a lot more water by having the snow melt as late as possible than we can in any of our surface reservoir features. So especially in the upper basin. For the lower basin, trends due to climate or dust or beetles, et cetera, are more of a slightly longer term impact. They've got a little bit of buffer with the main stem storage. Upper basin up here, it's really immediate. It's something where if we have a couple week change in snowmelt, it's a big deal for water managers and water users. So I'll talk a little bit about the snowmelt hydrograph and how that's changing. The hydrograph is really it's a depiction of runoff over the year. So this is January through December, and this is stream flow on the y-axis. And this is a classic snowmelt pulse, snowmelt-driven system, where you have a big pulse driven by the melt of snow sometime in late spring. If you go to the west slope of the Washington Cascades, for example, they have a two-peaked hydrograph. They've got a peak in November, December, where they get a lot of rain, and then a snowmelt pulse as well. So it's a kind of an interesting way to capture the normal dynamics of a particular river system. So how do we get a handle on this? So I mentioned the forecasts that Denver Water had trouble with a couple years ago. The Colorado Basin River Forecast Center is based in Salt Lake City. It's a Bureau of Reclamation outfit. And they issue short and long-term lead forecasts for all kinds of different locations in the Colorado River Basin. And their forecasts are critical for water management. And by water management, I mean dam operators who make decisions on when to close the penstocks or open them up, make some room in the reservoir for snow melt, or say, okay, we've got most of it, let's close it off, to ditch operators who are distributing water to their stakeholders, et cetera. These forecasts are based on a statistical index. And so we've got this network of snowtel stations. These are automated snow pillows, they call them, that actually weigh the snowpack at points up around the snow accumulation zone in the mountains. And here in the Roaring Fork, there's what, 6 or 7 of them, Jim? Does that sound right? So you get the idea. For the Roaring Fork Hunter Frying Pan zone here, about that size, only 7 of these spots. And so obviously one of these points isn't a very good representative of an entire basin as far as how much snow is actually on the ground everywhere. There's plenty of variability. But these sites are well correlated with stream flow. So an April 1 snowpack measurement at one of these sites is well correlated with how much water is flowing in the stream later in the snowmelt season. And based on this correlation, they make a statistical forecast. Well, that method is inherently based on this period of record. So here's a similar graph to what I showed earlier. In this case, there's the red line showing the observed snow water equivalent accumulation to date, and then a series of different colored lines, which are an ensemble forecast. There's a forecast assuming different weather conditions going forward. And as you can see, all of these different forecasts lie within that gray period of record boundary that exists for this station. So what this assumes, this method assumes that whatever weather we have coming this year there's going to be an analog for it in the past. There's going to be something within the period of record at this site that is going to look something like what's coming up this spring. If this spring doesn't look like anything in the past, or if it's, we call it not normal behavior, if we have a really wet spring and then all of a sudden it gets really hot, or something that's really out on the fringe, actually it could even be within the gray area, but just way out on the fringe of it, then this forecasting method really has trouble. So the power of this method comes when you've got a year that looks a lot like normal. The problem is, with a number of these different snowmelt drivers, that we're moving towards the boundaries of the distribution represented in the record. And that spells trouble for river forecasting. So one of the ways snow can vary is in the accumulation season. Before we even get to snow melt, the season that's rising up here on the SWE curve, this year that I'm showing here fairly closely mirrors the average accumulation, but there can be big jumps and steps in that. And then, again, these are just point measurements. So the question is, there's a couple ways that you can have not normal behavior. One of them that doesn't show up in these graphs at all is if you have a really strange accumulation pattern in the basin. So you may have exactly normal snow water equivalent at your monitoring site, that one point up in the basin, but if for some reason there's no snow up high and there's a ton of snow down low, then the snowmelt dynamics are going to be much different that year. So we're trying to monitor some of that, and in a qualitative fashion with some time-lapse imagery. So this is one of our study sites down off of Red Mountain Pass in the San Juans. And this is a 20-minute interval time-lapse over a little more than a month. And it's a little herky-jerky, but you can see some of the snow creeping around during wind events and whatnot. You can also see, if you look up here, high up in the basin, there's some bare patches, and a lot of bare patches down here, and then there's deeper patches. And so all of those are strongly driven by wind features. So you get the precipitation dumps essentially a uniform blanket of snow, and then the wind moves it around. And if you have a weird wind direction, then the snow is going to show up in a different spot than it normally would. And here's some really cool wind drifting coming up right here after this storm. And it kind of gives you an idea of exactly how changeable. So that was one day. So each flash is 20 minutes here. So that was one day, and you could get the idea of the amount of transport going on. Let's look at that again, because that's pretty darn cool. Okay, so this is just a little part of a little basin. So you scale this up and look at an entire river basin, and you've got these wind transport mechanisms pushing snow around all over the place. Then we get to the snow melt season. That last image, by the way, was taken from a site that's right down in here, looking up at this terrain. And this is a bigger view. So this is last summer's melt-off. And you can see the points that melt out latest are the deepest snow drifts. So, oops, look at that one more time. So if your snow distribution is normal, then all of this snow melt is going to aggregate through the basin and come out through your river gauge, and it's going to have a runoff hydrograph that looks normal, assuming you have the right amount of snow at the right time of year, and it has the right spatial distribution across the landscape. If you don't have enough snow, or too much snow, or it comes at the wrong time of year, or if the dominant wind direction has been different that year, maybe all the storms came from the northwest instead of the southwest or something like that, then those runoff dynamics are going to be different. Your forecast is going to have trouble, and the water managers are going to be flying by the seat of their pants. So when we talk about snowmelt, what we're really talking about is what melts snow, and that's the snowpack energy balance. And by energy balance, we mean all of the inputs and outputs of energy into and out of the snowpack. The big gorilla is shortwave energy from the sun. This is ultraviolet through near infrared, including the visible wavelengths that we like to look at. And then we have sublimation, which is basically evaporation straight from solid to vapor from the snowpack. Long wave, so this is terrestrial radiation. The snowpack is a great emitter. It actually loses a lot of heat straight to space via the long wave emission of radiation. Trees and clouds like to emit it as well, and so there's a balance going on there. Advection from precipitation, sensible heat from temperature, and this is what our instinct tells us melts snow, is temperature, because when it gets hot, the snow melts. But it turns out when it gets hot, the sun is out as well. And in reality, it's the solar radiation that's melting the snow, not the air temperature. So this graph shows for a 5-day period, again measured at our site in the San Juans, shows all the components of the energy balance. And the heavy dark line, that's the peak in the first 4 days at least, is the net flux. That's the total energy, and it's positive, which means it's going into the snowpack. And closely shadowing that is the net solar radiation. This blue line down here, are colors showing up okay? They're sort of a little bit washed out. This solid blue line here is the sensible heat from air temperature. So you can see it's dramatically lower. It's higher at night, of course. There's no sun at night, so you can get some warming. But this is a pretty warm period. The max air temperatures these days were in the upper 50s at 12,000 feet. So this is a warm period. Solar radiation is dominating. So because air temperature and solar radiation are so well coupled, because when the sun comes out, it also warms up, we can use air temperature as an index for snowmelt forecasting. But if there's a change to how the shortwave solar radiation is absorbed, say if you darken the snow surface with a coat of dust, for example, then all of a sudden that relationship between air temperature and how much snow melts has changed. And your forecast model can't handle that unless you're doing something with the energy balance specifically. So what we're really talking about with changing snowmelt, with changing the snowmelt drivers, is we're shifting the hydrograph. Okay, so this blue line is like that normal snowmelt hydrograph I showed earlier. We've got our spring peak. Here it is in this basin. It's in, looks like it's in July, with that snowmelt onset starting in late April. The red curve is precipitation. So we get most of the precipitation in the winter. That's the form of snow held over as storage in the snowpack that comes out later in the year. And this dotted black line is melt forcing. So by forcing, we mean what's driving the snowmelt and what's driving the energy balance. So there's not, and this is, again, dominated by solar radiation. So in the dark months, there's not a whole lot of solar, and melt forcing is pretty low. As we get into the summer months, that melt forcing goes up. And we've got an accumulation season where the snowpack is building and a melt season where it's melting away. So if we shift that melt forcing, and this is just a simple offset for cartoon purposes, but by either maybe some climate change has increased regional temperatures, maybe it's a late snowpack actually, and the snow is really brighter than usual late in the season. That could drop the melt forcing. If we throw dust on there or change the forest canopy cover, then we're changing that forcing, which can move the hydrograph. And the question is, what's the difference in that hydrograph? And the difference between those is the change in runoff or the change in storage. And that's a critical question. If a water manager knows how much we're going to shift the hydrograph in a given year, that's powerful information that they can use directly in their operations. And then another interesting question, and this is what Denver Water wants to know from us, is what percentage of that is due to pine beetles or due to dust, if any? So this is kind of the background of how this research question has come about. So for the past number of years, we've been pretty heavily into studying dust on snow, and it's been a good time period over which to do that. We've had a number of striking dusty years. This, I believe, was 2009. This is our upper study plot, again, off of Red Mountain Pass. The effects are pretty obvious of the dust darkening the snowpack. I'm sure most of you have experienced some of the dust storms coming in. Here's April 3rd in Silverton, sort of apocalyptic looking. Same day in Telluride. Same day in Crested Butte. Same day up here at Goodwin Green Hut, where Jim and I actually were on a hut trip and jumping around like crazy when this sky came in. And we actually had to dig the dust off the snow in order to get our meltwater for cooking with. Anyways, there's that layer from that storm. That's the April 3rd storm. There was a series of storms earlier in the season and a series after that that made 2009 the heaviest dust year we've been able to observe over the past almost decade now. So here's how it works. So that again is a snow surface in the background. And the graph is what's called a spectrograph. This is the reflectance of the surface, snow in this case, across different wavelengths. And so the visible spectrum is here in the rainbow from 0.4 to 0.7 microns. Near infrared is longer wavelengths, and we get some UV down here. And you can see the biggest impact of dust is here in the visible wavelength. So when your eyes tell you that there's dust on the snow, they're actually doing a really good job of telling you where the dominant impact is spectrally. There's also some impact out in the near infrared, but basically you take the solar irradiance, multiply it by that change in reflectance, and you get how much extra energy is going into the snow. And it can be a doubling of solar input. And as I mentioned, that solar is already the dominant driver of snowmelt. So if we're doubling that, we can see some pretty extreme melt rates. This is a whole field of research, spectroscopy, and you can look at different surfaces with a spectrometer and get all kinds of different properties out of it. If you look at this surface and look it up, what you get, if you look that up in a textbook, it says it's dirt, not snow. And so again, we get some pretty striking patterns over the landscape. 2009 is really was the money year for eye candy shots like this, but really just pretty impressive. So we can do some computer modeling to tease out exactly what that extra forcing from the dust is doing. So here's 6 years of measurements and model results at our study site in the San Juans. The red curves are modeled snow water equivalent through the melt season. So going from peak peak accumulation all the way to melt out. And there's some black dots in there that are our observations. So our model is doing a great job of simulating what the snowpack melt out looks like. The blue lines are what happens if you tell the model that there's actually no dust there and that the snowpack is clean. And the difference in where these curves melt out, where they hit zero snow, the difference in days tells us how much longer the snowpack would have lasted if the dust wasn't there. 2005 through 2008, we're looking at about a month. So think about that, a month longer snowpack. So the snow is our biggest reservoir. If we can hold it on for a month, that's a month longer into the summer season that we have snowmelt trickling into the rivers. Also, if you think of how drastically snow changes the landscape, even dusty snow is well, usually much brighter than what's underneath it. So we're talking over a large area, we're changing that Earth-atmosphere interaction from a bright surface underneath the atmosphere to a dark surface underneath the atmosphere. That has important effects on air temperature regionally and downwind. A month different. 2009 and 2010 were close to 50 days. So this is a massive, massive perturbation, not just to the snowmelt system and the hydrology on which we all depend, but to the Earth system in general. This is a massive regional perturbation. So here's this graph again. And it's basically the same thing our model is doing. Here's our peak snow water equivalent, and there's our meltout. And we can look at the difference between where the average was, because we were pretty much at average at the right time of year. We can look at the meltout difference, and it was about 35 days at this site in 2009. So this is not just This is not just computer modeling. This is manifested in the observations. So we've done some broader scale modeling looking at the whole upper Colorado River Basin. The colors here represent the change in meltout day, that number of days change due to dust. And we're seeing, this is based on 2005 to 2008 dust conditions. And we're seeing at our measurement site right around 30 days, which is good because that's what we saw there. But we see some variability around the basin. I want to draw in particular your attention to this sort of band right through here. I'll let you stew on that in the background for a while. I'm going to come back to this. When we aggregate this change into a hydrograph, this is a hydrograph at Lee's Ferry, which is right above the Grand Canyon below Lake Powell in Arizona, and is the dividing point between the upper Colorado and the lower Colorado River Basin, the legal dividing point. And the red curve here is the hydrograph over the past 88 years, actually prior to 2003, that closely matches what we observe at Lee's Ferry. If we clean up the snowpack, we get the blue curve. So right now, under our current dusty conditions, relative to a pre-disturbance case, and I guess I should mention that the majority of this dust is coming from the Four Corners region, and there's been a massive uptick in the amount of dust coming into the Colorado mountains since the late 1800s, coincident with the introduction of grazing animals to the Colorado Plateau, and disturbing the biogenic soil crusts that naturally occur in those regions and making lots of fine sediment available for wind transport. The current disturbance mechanisms out there now extend quite a bit beyond just grazing animals, but that was the initial disturbance. So if we clean it up to pre-disturbance conditions, we get this blue hydrograph. So currently, we're having a 3-week earlier snowmelt peak, a steeper, what's called rising limb, the rising edge of the hydrograph. Steeper means that your snowmelt peaks in a much shorter time, and which is something that's very difficult for water managers to deal with. They like a more protracted meltout. And very interestingly, the difference between these two curves shows that we're getting about 5% less annual runoff in the river currently than prior to the disturbance and the ginning up of all this dust. That's this graph on the right. 5%, it kind of doesn't sound like a lot, but in a system that's already over-allocated, we saw the supply and demand curve earlier, 5% is a huge amount. It's twice what Las Vegas gets every year. It's 18 months for Los Angeles, and it's about half our treaty obligation in Mexico. So that puts it into perspective. That's a lot of water in this system. The percentage varies from year to year in our model estimation. So from 2.5% to 7%. 7%'s, this is a lot. I mean, this is on the order of what climate change projections are suggesting for 2100. So this is a big change. Again, these results are based on dust loadings observed prior to 2009. 2009 was a game changer. We didn't even know we could get that much dust in the snowpack here. So we've done some recent modeling that I'll show you in a little bit. So dust is clearly a major player. When it exists on the snowpack here, it has big impacts on snowmelt and on how much water ends up in the river. The pine beetle infestation is pretty widespread and is doing dramatic things to the forested landscape that involves basically removing the forest canopy over large swaths of terrain. This is up north of Steamboat Springs, actually, and so you can see all the gray areas back here with a little bit of, I think that's some aspen poking around in there, but basically the entire lodgepole stand is gone. So there's a whole bunch of different bark beetles. There's spruce beetles, there's a couple different pine beetles, etc. The big infestation we're having now in Colorado is Mountain Pine Beetle. We've had some spruce beetle impacts going on down in the San Juans. I don't think they're quite calling them epidemic status yet, but you'll see in a moment that the pine beetle one is definitely a pretty massive event. So the mountain pine beetle has this kind of infestation trajectory, if you will. You start from a green forest in the first year that the pine beetle attack starts. And then there's this red phase where the needles turn red, but they're still on the trees, kind of a rust color. And you start getting lots of litter fall as those needles fall off. Then we get what's called a gray phase, which is just the standing dead, no needles left. And then some tree fall, and then a regeneration phase, which can take quite some time. Here's the progression over the past 15 years. And if it looks like it's bloodstained, I guess it probably should. 4 million acres just in Colorado have been hit by the mountain pine beetle. And in 2010 alone was 400,000 new acres. And you can see the different colors in this map are different periods, time periods. So you can see there's been sort of a shift towards the Front Range now after all of the lodgepoles in Summit County and Routt County got eaten up. The beetles started moving into the Front Range. So we're seeing a lot of the ponderosa pines in the Front Range get hit now. So pretty massive impact. Jim Baylog, who does a lot of time-lapse photography as a National Geographic photographer, our partner on the snow time-lapse that I showed earlier, has done a project for the Forest, who's now part of ACES, looking at some of the pine beetle impacts. So this is a time-lapse of an infestation in Rocky Mountain Park. And it's a pretty quick transition in this case from newly infested red phase to gray phase. And you can really see the trees start to lose their moisture and will to live, if you will. So as this is happening, start thinking about, there's some snow for you. So start thinking about what changing the canopy like this does when you start throwing snow into the system. It's going to run backwards now, which is kind of instructive for picking things out. So when this happens to one or two trees, it's a pretty local impact and maybe not such a big deal. When it happens to the entire forest, there's obviously a massive shift in what the canopy's doing. And so we've got the snow energy balance that I showed earlier. And on top of that, in forested regions, we've got the forest energy and water budget. So we've got energy flows and then water flows through the system. So we've got inputs from precipitation, snowfall or rainfall. Some of that runs off into the streams. Some of it goes into the soil, gets soaked up by the trees, transpired. Some of it goes into deep groundwater. There's different ways it can interact with the tree itself. So if you have a full canopy, you get a lot of interception. Even if it's rain, a lot of that rain stays in the canopy and drips off slowly. If you don't have much canopy there, then you can't intercept much. So there's a whole host of impacts here, and I'll run through some of them. And I hope what I want you to get out of this segment is that this system is incredibly complicated when you start talking about hydrologic impacts of changing the forest on a massive scale. So we have impacts on accumulation and melt. We get more snow that falls through instead of being intercepted and sublimated. We get faster melt rates because there's more solar radiation getting through now. And then when the trees are healthy, they're sucking up quite a bit of water and transpiring it as part of their metabolic process. That's effectively shut off right away as soon as the trees are hit by the bark beetle. Here's a couple of hemispherical photographs looking up through the canopy. These are different locations, so it's a little bit misleading. There's slightly different stem densities there. But nonetheless, I think you can readily see that, you lose or you gain a lot of light coming in when you lose that canopy. And by analogy, you lose a lot of intercepting area. Again, here's the change in amount of solar radiation that comes through. Again, these percentages don't seem like a big change, but remember, we're talking about the dominant factor by a factor of 2 in the energy budget of the snowpack. So if you're adding more solar radiation, you're doing a lot to the snowpack. Accumulation phase, there's our different living, there's green, red, and gray phases. Gray phase behaves a whole lot more like a clearing in terms of the amount of snow that shows up on the ground than the rest of the forest does, even though you still have a lot of sticks standing up there. Importantly, even the red phase, if you have a year of red phase, you still get a lot of interception, and therefore can lose a lot of snow to sublimation. Here's another time lapse. This is a spruce beetle attack. This tree here is the one that gets hit. Towards the end of this, you'll see some snowfall come in, and I want you to look at the amount of snow that's intercepted on the surrounding trees versus this tree that gets hit. See if I can back that up a little bit. So this right here is the biggest impact. Oops, now I've done it. Another thing that happens is we change the albedo, and this is of the snowpack, and this is analogous to what happens with dust. So in a red phase pine beetle forest, we get a lot of tree litter landing on the snowpack, and that can have a big impact on the snow albedo and therefore the amount of solar radiation that gets absorbed. So this is, let's see, the right photograph is from a healthy green forest, still some tree litter, but here this is from a red phase forest, much darker snowpack. It's going to absorb a lot more incident solar radiation. I mentioned the tree water use. This is an interesting study that, so the green bars and dots are from a controlled, just green tree, and they're measuring sap flow. They girdled a couple trees, so they cut the bark all the way around it and monitored those, and then they found some that were pine beetle infested. And basically within 3 weeks of pine beetle infestation, transpiration is gone down to about 50%. So this is a pretty quick impact on the amount of water being pumped out of the system by the trees themselves. So think back to the water budget. We've got all the different pathways that water can flow through the forest and end up in the stream maybe. We've now just basically chopped off the big pipe that sends water vapor into the air through the canopy. So that's a big impact. All right. So this is what I mean. There's all kinds of confusing offsetting factors. I'm not going to go through all of these. The top bunch is for red phase. The bottom bunch is for gray phase. And we've got some changes in albedo, the snowpack. We've got some changes in how much solar radiation comes through. Changes in wind speed, I didn't talk about that, but if you get rid of the canopy, the wind speed's higher, and that affects how much air temperature affects the snowpack, and how much sublimation losses happen from the ground. Change in long wave, wet forest canopy gets a lot more energy radiating to the snowpack than a dead canopy does. So the question is, how do these balance out? What we really want to know is, if we annihilate a forest in a basin with the pine beetle, does that change how much water is coming out? And with all of the impacts that can have on the eco-hydrology, on the soil development, and on water users downstream. And it turns out that these balances aren't constant even within an individual tree stand, that they're going to vary by the position of a particular stand in the landscape, by the composition of a basin's terrain components of the type of forest that's there, how well mixed it is, whether it's 100% lodgepole or whether it's a mixture of species, and the snow year. If it's a big snow year, there's going to be different impacts than if it's a light snow year. And so I think that helps to explain why in a number of studies that have been done recently on the Colorado epidemic, that we've not been able to detect any hydrologic response from the pine beetle infestation. This is an interesting graph here. This is stream flow in two different rivers that are well correlated to each other. And one of them, both of them were unaffected by pine beetle until 2003, and then one of them got hit. East St. Louis got hit. Sorry, other way around. East St. Louis was okay. Brush Creek got hit. And you can see there's a pretty coherent relationship between these two streams. You know, when Brush Creek's at 10,000 CFS, East St. Louis tends to be at about 1,000, and that relationship holds over a wide range of flows. The black circles are the pre-infestation ones. Then there's some colored ones in there that are after Brush Creek got hit by pine beetles pretty heavily, and we're talking most of the basin. Still right on the same relationship, so no detectable signal there. Unfortunately, in 2009, East St. Louis got hit also, so we lost the control study there. So we can't keep doing this experiment with these two basins. So there's some offsetting factors that went through in the previous graph, but it may be that there is a signal that will emerge after a good period of time. Fortunately, we can't monitor that at these two creeks anymore. But we're not seeing those results just yet. So I alluded to the basin and stand dependency. Here's two pictures they're nearby. They're in Glacier National Park, actually up in Montana. Or the right picture actually shows the international boundary. So I guess it's Waterton Park and Glacier Park. The pine beetles don't care about politics. But you can see two different infestation patterns here. On the right is a little more splotchy versus the left picture is a little more uniform. There's still some splotchiness there. So we've got this pattern of infestation. They're going to have different impacts on the hydrology. One big sleeper is what we do in response to pine beetles. So interestingly enough, a lot of the analogy people use for what might happen to the forest based on a pine beetle attack comes from research that's been done on clear cutting. And clear cutting has a big impact on the hydrology. You see much higher accumulation, and you see much faster snowmelt. It's a very clear signal in the streamflow hydrograph. But we're not seeing that signal out of even heavily impacted pine beetle forests. But if we go in and clear cut them, then yeah, you can bet we're going to get a signal. So there's a lot of almost panic-driven management response to the large infestations, and there's a ton of clear cutting going on without even really using any of the forest products that come out of it. They're just piling the stuff. So you can maybe read between the lines on how I feel about that. There's a whole, there's a forest management paradigm behind all of this, but if you want to get a signal out of a pine beetle infestation, clear cut the forest and you'll definitely get one. So we also have some accumulation and melt variability in the snowpack itself. And so we've got, I alluded to the fact that a different snow year will have different impacts on the hydrology coming out of a pine beetle impacted forest. How the snow accumulates, like I was talking about earlier, is going to impact that variability. Okay, so we've got dust and we've got pine beetles. And it turns out we got climate change also, and this is happening. This is global temperatures from observed networks. This isn't a model. Those trends manifest themselves regionally as well. The top is temperature, starting in 1890, going to 2010. The bottom graph is precipitation, which doesn't show really any trend, although it appears that the variability year to year has kicked up a notch. I can see that. I don't know if I'd call that a trend in the variability yet myself. Nonetheless, the temperature signal is clear, the precipitation signal is not. So how does this impact the snow? Going forward, the models definitely project strong regional warming for the Colorado River Basin. This is a particular model for a particular carbon emission scenario. There's a pretty high one, but it turns out that our actual emissions are above that anyways. We're looking at order 7 degrees C in this region by 2100, which is something that we need to avoid if we want to recognize any of our landscape. So we're seeing some shift in snow accumulation and snow melt. This is a study done in 2006. The color of the circle, red, means a decrease in 1st of April snowpack. Blue means an increase, and the size of the circle is the size of that trend. So broadly across the West, I don't know if you can see these lines. Here's the coast, Washington, Oregon, California. So we're over here. We see a bit of a mixed bag. California's got a really interesting signal with this big increase in the Southern Sierra. This is a whole nother talk. But we're definitely seeing changes in the 1st of April snowpack. So climate change can have direct impacts on what the snow does. We get later accumulation and earlier melt, so the snow season gets compressed. We see an increase in rain events. Snow that used to come in maybe close to freezing, you warm it up just a little bit. This is a bigger deal along the coast, but we can get this too. You'll have a rainstorm instead of a snowstorm. Precipitation intensity appears to be going up. You put a lot more energy and water vapor in the atmosphere, your weather events are going to get more intense. Projections of climate change run through hydrology models suggest a 10 to 20% reduction in Colorado River flow by the end of the century, which, remember, 5% is a big deal. 20%, catastrophic. However, in the short term, these indirect effects, and I think you'll see what I'm getting at here, the effects of dust, the potential impacts of pine beetle, and changes in snow accumulation patterns are likely to be the biggest component of the climate change signal that we see manifested through the snowpack. Here's what I mean by anomalous snow distribution. So this was the snow water equivalent over the state of Colorado and a little bit beyond in March of 2010. And it would take a little while to zoom in on this, but take my word for it that we had a lot of low elevation snow late in the season in 2010. And again, getting back to the forecasting problem, our snowtel sites are in a certain elevation band. So this shows by different states. The max elevation in the state is this top line. The minimum elevation is the bottom line. And the range of elevations of the snowtel sites in those states is shown by these plots, box plots. And so you can see, let's see, Colorado's the third one. So we've got a range of monitoring here that doesn't get up in the highest mountains and doesn't get down in the lowest mountains. So if we have a low elevation snowpack, say late in the season, the bulk of our snowpack is down here, we don't see it. Or if we have early melt out and we melt out and there's still a bunch of snow above the snowtel network, we don't see it. And the forecast models can't predict anything. So if a climate change driven year means that we have a different storm track and we have different snow accumulation patterns, then what our snowtel network is telling us is not going to necessarily manifest itself in an accurate forecast. And there's plenty of uncertainty as to what exactly the impacts on the ground of climate change will look like hydrologically, much less in many other sectors. But we know it will produce things that don't look like the normal period of record. So I'm going to tie it back into dust and pine beetles here because there's a climate change signal manifested in these phenomena as well. Dust emission from the desert regions is strongly tied to drought and the cycle of annual vegetation out there, as well as soil moisture. Increasing temperature will reduce plant cover and increase dust emission. This is a recent study done by some of our collaborators. So we will likely see more years like 2009 in the future than years like 2005, which had very little dust. So I mentioned that we've been doing some modeling looking at what that might look like. The black, we saw the blue and red curve. The red is kind of normal. Blue is if we clean everything up. This again is river flow at Lee's Ferry. The black curve is if we use dust loadings like 2009. So again, we get another massive shift in when the snow melts out and runs off through the river system. Less of a decrease in total volume of flow in the river, which is interesting. Basically what we've done here is shifted the snow melt just using dust earlier in the season when there isn't a whole lot, when it's not really that warm and you can't drive the evaporation and transpiration that is the cause of that change in runoff volume. However, if we warm the climate up a bit and shift the hydrograph earlier, we will start getting major declines due to that different dust loading. So here's the 3 different dust loading scenarios, but in a 2050 climate showing a range of potentials, and 2100, and things start looking pretty grim. Certainly at the high range, if you start including dust, at the high range of the projected estimates of river flow declines late in the century. Bark beetles, there's a number of different factors that influence whether a bark beetle infestation, these guys are a natural part of the system. It's not like they've been created anthropogenically and they're now munching through the forest. They're a natural part of the system. They're a natural disturbance agent. But if you start warming things up, all of a sudden, we don't have the cold temperatures to keep them in check. Some of these little buggers switch from a 2-year to 1-year life cycle, so they can really ramp up their infestation. Look what's going on up in British Columbia. Massive, massive disturbance in the Fraser Basin up there. So we're getting a lot of information out of what's happening up there. So as we move forward, we're going to likely see further infestations from the pine beetle and other bark beetles as well. And if that longer term brings a strong hydrologic signal, then it'll come out here. So I mentioned, hopefully you've all been thinking about what's going on in this region where we see the least amount of dust impact. Well, that's the forested belt in Colorado. And dust is having the biggest impact on solar radiation, but if you have a forest canopy, solar radiation is not as big a deal as it is in the open. If we throw the pine beetle on all of those and get rid of the forest canopy, maybe there's a mixed signal from the pine beetle infestation itself in terms of the hydrology, but you start throwing dust in there, and dust can have an impact in those areas where it didn't before. So we're looking at multiple interweaving impacts here. Climate warming helping cause some of the dust and pine beetle problems, and then those two interactions creating a much more volatile snowmelt scenario. We're doing some modeling to try to tease out exactly if we clear cut or if we have a big infestation and change the forest, and we do different levels of dust. Hopefully this can answer some of Denver Water's questions and the River Basin Forecast Center's questions as to how they can be adjusting their models. So we've got a distribution of sites around the state, and hopefully we'll be seeing some results from that in the next year or so. So back to Boulder Creek, spring of 2010 and the Red Lion Bridge. Again, the media said it was hot. Well, what the media didn't recognize, this is what it looked like on that flood day up in the Boulder Creek watershed. That's my brother. We were skiing on South Arapahoe Peak. Dust everywhere. And our modeling study will help us answer this question, but I'm going to go ahead and project right now that what it's going to say is that if we didn't have any dust, the news media would have been saying, people are having a great time splashing at Boulder Creek to beat the heat. Not. The temperatures are taking out the Red Lion Bridge. So dust was a major player there. We know that for sure. Thanks. I'd be happy to take any questions that anybody has or discuss anything. So.